Today's lecture is called Signals, Cables, and Impedance. The topic is music technology hardware, like cables, preamplifiers, electric instruments, amplifiers, and speakers. All of the wonderful hardware devices that you'll encounter if you're going to be a producer or an audio engineer. So if one asks you about today's topic, you say, yeah, we talked about music technology hardware. We talked about cables and signals that go inside of them. It's an important topic. Maybe not the sexiest topic. Nonetheless, even if you're a producer who mainly spends their time behind a DAW,
Eventually, you got to get your cables out and plug things in.
so it is helpful to know what's inside the cables and what the differences are and the various cables that you'll encounter in the pro audio environment. Music technology hardware, like cables, and the point being that if you're going to be a producer or an engineer or a professional music technologist, then it is critical that you know these things. Okay, a few objectives so we know what we're headed towards. After today's presentation, you should be able to identify 4 analog signal types, and I'll go through those for you. You should be able to retell in your own words or explain to a friend of yours
The definition of voltage and amperage.
but you've almost certainly encountered these words, right? You look on the back of your adapters or you look on some electronic component that you bought, you might see a voltage or an amperage listed there.
Then we'll look to differentiate between the various cable types, including unbalanced, balanced, and speaker.
And then I'll briefly describe the concept of impedance and then show you what to do when it comes to setting up amplifier and speaker configurations. So that's the plan. We're going to talk about signals, cables, and impedance. This particular topic trespasses on a little bit of science that we should clarify. So, of course, we're talking about electricity, which is the water-like flow of electrons along a conductor like copper. So essentially, it's this: the baser nature of reality is comprised of atoms, and atoms are like miniature solar systems, wherein they have a cloud of electrons orbiting a nucleus. And those electrons are volatile, meaning that they can shift from atom to atom. And indeed, if you have a buildup of an electron charge, which is called a negative charge, you can actually get a flow of electrons from one area to another. And of course, the most spectacular example of that is lightning, right? But you walk around your carpeted house with socks on and then touch a metal doorknob, you might shoot lightning out of your fingertip in the form of static electricity. Now, what's happening there is just an exchange of electrons. And this could be harnessed and controlled if we use a conductor like copper. So if you imagine a buildup of electrons on a conductor like copper, and then you touch the other end of the copper wire to another conductor, it'll close the circuit and the electrons will flow. That's essentially what's happening with electricity, a flow of electrons. Okay, so that means that we should be familiar with a few units, right? And those units are voltage, amperage, and then ohms. So it looks like this. This funny little cartoon explains it nicely. That word voltage or volt is the potential for a water-like flow of electrons. It's not the flow itself. It's just, hey, are you guys ready? I'm ready. Are you ready? I'm ready. Let's go, let's go, let's go. It's the potential. So for example, a wall outlet has a potential or a voltage. So in America, our wall outlets are 120 volts. That doesn't mean that it's shooting 120 volts of lightning out at you at all times. It's just ready to go. It has a potential for electricity. And you can also think of this in terms of a battery, like a 9-volt battery. It's got 9 volts ready to go, but it's not actively doing anything. It's just potential. It's like holding a rock over a precipice or a cliff, right? And I can drop this and create kinetic energy at any moment, but right now it just has potential energy. So that's what a volt is. It's potential. And then amperage is what we call once it actually starts to flow. Okay, so now we connect the 2 points along a conductor, right? We touch this piece of copper to this piece of copper, and now the electrons can flow. That's the amperage. So all things being equal, 1 volt creates 1 amp. But as it happens, there's this thing called impedance, sometimes called resistance, and it's measured in ohms. So you can see here, the ohm character has the lasso and is squeezing the wire together so as to create resistance, right? And the volt's shoving. It's like, come on, go amp, go amp. But the amp can only travel insofar as the resistance allows it. So things that create resistance are the length of the cable, the quality of the substance, how many operations the electricity has to perform along the way, right? If the volt shoves the amp and then the amp has to go to this speaker enclosure and operate its speaker cone, and then after that speaker enclosure, it's got to go to another set of speakers and operate that speaker cone, that creates resistance, right? It has to operate at this speaker and then operate at that speaker. So that's why if you have any experience with speaker systems, you might have noticed this word ohms before. And why it's important is because the electricity is being stymied by the duties that it has to perform, or the length that it has to travel, or the quality of the wire, or the quality of the devices. So in summary, voltage is the potential. You ready to go? I'm ready to go. Let's go. Let's do this. Voltage. Amperage. That's like the water in the garden hose. Like, all right, I'm finally going. I'm finally flowing. 1 volt equals 1 amp, except that resistance has an effect, and that effect is usually to decrease the amperage in relationship to the voltage. Okay, that's the science class portion. And I'm telling you all of this because we are talking about analog audio. Remember, in one of the first lectures, I explained that analog audio is jolts and squirts of electricity that are perfectly analogous to twangs and pings of sound. So, for example, this microphone is taking the mechanical sound energy of my speaking voice and converting it into electricity. And the intensity and the shape of this electric flow will be perfectly analogous to the intensity and the shape of the sound flow. That's analog audio. That's what's coming out of a guitar. That's what's coming out of your speaker cables. That's what's going through your headphone wires. Jolts and squirts of electricity that are perfectly analogous to twangs and pings of sound. And those jolts and squirts of electricity are beholden to measurements such as voltage, amperage, and ohms. Okay, so in the realm of pro audio, if you're going to be an engineer or sound producer, run live shows, you're going to encounter 4 basic kinds of analog signal. And they are microphone, instrument, line, and speaker. Now, the reason why I went through all of that voltage and amperage business is that what is actually different about these signals is the intensity of the voltage, or by derivation, the intensity of the amperage. So these different analog signal types vary in how intense they are at the level of electricity. And it's basically like this. Microphone signal is super weak and speaker signal is super strong. The weakest signal is microphone signal. Now I have a whole module planned on microphones, and in that module, I'll explain the differences between dynamic and condenser mics. And essentially, for this topic, it's enough to know that dynamic mics are the weakest of the weak. They're producing only 1.5 millivolts. Okay. So let's define our terms here. Let's go to the internet. VOLTS, millivolts. The heck is that? So 1 millivolt is equivalent to 0.001 volts. Okay, so let's look at how the term works. If we put in 1,000 millivolts, that's equal to 1 volt. See how that works? That's where that milli, that prefix there, is 1,000th of a volt. So, we're not starting any fires here. Consider that a 9-volt battery, right? That would be 9,000 millivolts, right? That's a veritable torrent of electricity compared to what do we got here? 1.5 millivolts is 0.0015 volts. Okay, so your microphone, right? Your dynamic microphone is creating only 1.5 millivolts. That's a baby signal, right? That's a tiny little stream of electrons. Now, usually in the studio, you want a little more signal than that. You want a little more clarity and high fidelity. So a condenser mic is a good choice. And indeed, that's what I'm speaking into now. It's fairly good at good, detailed, and translatable audio. It's stronger, but, we're not exactly starting a fire here yet. 70 millivolts. So 70. So now we're at 0.07 volts. So this is a tiny signal. Tiny signal. So the microphone, one of the 4 basic analog signal types, that's a tiny little baby signal. Okay, and then moving forward, we have what's called instrument level. It's a little stronger than microphone level, but not much stronger. And of course, you're going to have different instrument levels between your instruments, but we can think of an average here. If you play an open D string on a guitar, all right, that just generated about 425 millivolts. So what do we got in terms of voltage? So if we put in 425 millivolts, right, we're getting up there, almost a half volt. Not real strong yet, but significantly stronger than our little baby microphone signals. Okay. You'll also encounter this word in the pro audio world, line level, which is stronger, again, than instrument level. And it ranges from about 750 millivolts to 1.5 volts. So finally, we're up over a volt. And this is the signal that is used to route your analog audio through your mixing board, back out to effects processors, back to your mixing board, and then bust out to your amplifier before it becomes speaker level. It's sort of a medium-sized, robust signal that is useful and large enough that it's not going to be corrupted by interference. The problem with these little baby signals, microphone signal, 1.5 millivolts, and the slightly stronger instrument level, 425 millivolts, is that they're sort of on par with some of the electromagnetic interference that you can encounter from radio signals, cell phone signals, television signals, can interfere and corrupt those little baby signals. Your cables are essentially antennas in a different guise. So we'll come back to what we do about that right after I describe speaker level, which is the 4th, final, and largest of the 4 analog pro audio signals. Now, of course, this varies speaker system to speaker system. But if you can imagine you're using a professional PA system, say you're putting on a show, a DJ show, or a band show, and you got nice big speaker arrays, maybe a subwoofer, monitors, and power amplifiers that are generating something like 1,000 watts, maybe a couple power amplifiers. That's pushing 90 volts, about. Okay, so you see that this isn't even in the same neighborhood, right? 90 volts, let's see what this number is, right, is 95,000 millivolts. Okay, so your speaker level can start a fire. This is significantly, you can throw your microphone in the bathtub. I'm not recommending that you do that while you're in it, and you're not going to electrocute yourself with a microphone as long as it's not plugged in. It's generating voltage, but it's not generating a voltage that is dangerous. Where you get up into speaker level is like, okay, this is a pretty strong flow of electricity. I tried to do a scale with this picture here, signals to scale. So notice up here in the top left-hand corner, we got that's a microphone and a little microphone cable, tiny little signal, and then a little bit bigger, right? We have the instrument level, like this electric guitar, and then slightly larger and medium-sized, robust signal is this line level. You might see this on, a line out on your computer, or a line out on some device. Some audio device, maybe a digital keyboard, has a line out. Like, what the heck is that? Well, that's a pretty nice, robust signal that you can send and route and know that it won't be corruptible like these two. We still have to come back to what to do about these baby signals, and I'll explain that in a second. Now, this isn't quite to scale. If this was actually to scale, these speaker cables here would be like, 10 times larger than this slide can accommodate. But that's sort of the order of operations. So let's just let that detonate in our minds, right? If you're going to be a producer, an engineer, recording engineer, live sound engineer, you're going to encounter analog signals. There's no way around it. And in this realm, there are 4 analog signals: microphone, instrument, line, and speaker. And they are only different insofar as the intensity of the electricity that they carry. They're all carrying analog audio. And this picture here sort of shows you the difference in voltage. Okay. The microphone and instrument levels, they need to be beefed up to line level in order to operate within a mixing board, in order to be routed to signal processors, etc., in order to be accurately converted to digital via your analog to digital converter. If you have an analog to digital converter at the front of your DAW, the first thing that happens is the first thing that happens on all mixing boards on Earth, is that these round circles here with the 3 holes, or these quarter-inch phono inputs, those are the gateways to a device called a preamplifier. Preamplifier. A preamplifier converts microphone and instrument level into line level. Preamplifiers beget line level. Now we're in business. Now we got a nice robust signal that, though it's not going to start a fire like speaker level, it's strong enough that it's not corruptible. Okay, if you are an instrumentalist and you play guitar or bass, a preamplifier is built into your amplifier. So I try to find a picture of an amplifier that had the knobs, but on the far right here it says master volume. That's the amplifier properly. But if this picture went further to the left, there should be a gain knob, a knob that indicates gain. And that is referring to the preamplifier, which is to say, let's convert like that little weak signal coming out of an electric guitar. The amp's like, all right, I gotta first beef that up so it's proper and useful. And then and only then can it be super amped up to speaker level. And that's what's going on with your mixing board. That's this first stage up here, is these microphone inputs and these phono plug inputs are creating line level. And there is one more device before I go back and talk about the cables, and that is the amplifiers. So similar to how preamplifiers converted instrument and microphone level to line level, amplifiers convert line level to speaker level, right? They're really beefing it up. Now this signal, this analog audio, is capable of shoving back and forth on a speaker cone so as to recreate the initial mechanical energy of the sound as it was originally. So my voice is in my room here generating sound. The microphone is transducing that sound into electricity, And then on the other end of the chain is a speaker that reconverts the electricity into sound energy. And that requires more voltage, and that more voltage is garnered through the good old power amps. So here it is in summary: microphone and instrument, very weak. They need a preamplifier to become line level. Line level, nice and medium size and strong, can be routed around your mixing board and manipulated, is then routed out to an amplifier, and that amplifier sends speaker level to the speakers. Huge 90 volts, powerful analog audio. Okay, so that's what's going on at the level of electricity and the differences between the signals. Now we should take a look at some of the cables you'll encounter. If you ever have gone to a DJ show or to a live musical performance, you may have noticed that the entire environment is festooned with pro audio cables. There's cables on the ground, cables on the speaker. The instrumentalist has cables coming out of their instrument. Cables, cables, cables. All right, cables everywhere. Okay, there are three basic types. They do have more than one name apiece, but I'm going to try to keep this as simple as possible so I can explain without confusion. There are unbalanced cables, balanced cables, and speaker cables. Let's take a look at each one in turn. The unbalanced cable has two connection points. So if you take your unbalanced cable apart like this one here, there's two tangs, metal tangs, and affixed to each one of those tangs is a wire. And then if you go to the plug itself, notice that there's a sleeve of metal material separated by a ring of plastic, and then a tip, which is also metal material. So that means that the devices make contact with this tip, and they make contact with the sleeve, and it's separated by this ring. And then here you have two cables, right? So that's what an unbalanced cable is. What is it transferring? It's transferring signal, like your analog signal, and it's transferring a ground. And this picture here shows you what the ground is. This is a mesh that surrounds the inside of the cable. And that mesh is designed to preserve your analog audio from the bombardment of cell phone signals, radio signals, television signals, CB radio, the electromagnetic spectrum. So, common music technology applications for the unbalanced phono plug is for instruments. That's what a guitar is plugged in with, or patch cables. It's unbalanced. And then the next cable type will explain what this balance, unbalance differentiation is all about. So balance cables, unlike the unbalanced cables, have three connection points. So here's a microphone cable. It's the quintessential, the basic, most essential example of the type, and the type is balance cable. Notice it has three connection points, 1, 2, 3, to be contrasted with the two connection points on offer in the unbalanced cable. Okay, so what's that extra wire for? That's weird. That means that instead of just one signal and ground, notice that in this diagram here, this gray barrel, that's the shielding, right? That's the mesh. That's the protective layer. But there's this other signal. Now, look at these weird blue and red waveforms. What this is telling you is that the analog audio in each one of these wires is 180 degrees out of phase with its neighbor. So this sound is compressing, while this one is rarefacting. Now this one is compressing, and this one is rarefacting. They are polar opposites of one another. Now, what is amazing about this is you can send the signal much, much further than you can with unbalanced cables. You get a guitar cable that's longer than 25 feet, it's essentially an antenna. But you can send balanced cable signal something like 350 feet before it becomes a problem. The magic maneuver is that any noise accumulated in its journeys along that 350 feet will be canceled via the property of phase once the signals are resummed at the other end. So what happens with a balanced cable is when you plug it into your input, that input unit sums the two signals back into one, thereby canceling out any noise. It's amazing. That's a balanced cable. 3 contact points. So here's a balanced cable dissected, right? We got 2 cables carrying polar opposite versions of the analog audio, and then we have the protective mesh. You won't only encounter balanced cables in the realm of microphone cables. You might also encounter phono plugs that have 3 contact points, right? This is tip, ring, and sleeve, TRS, right? Be contrasted with just the tip and the sleeve, or tip and ring. Yeah, I believe that these are called TR cables, and these are TR cables, and these ones are called TRS cables, tip, ring, and sleeve. If you look carefully at your headphones, right, if you have just a set of analog headphones, you'll notice that they're just miniature phono plugs with TRS. So if you look at standard headphones, we got TRS. What is peculiar here is we're not carrying mono in a balanced fashion. We're actually carrying 2 unbalanced signals, which is a game that balanced cables can play. They can pretend to be unbalanced cables and carry stereo. It's just you have an unbalanced left and an unbalanced right, 3 contact points, one of them is ground. Now, if you look at your headphones and you have 3 rings, right? You have TRRRS, tip, ring, ring, sleeve. That means that that cable is also carrying a microphone signal. It's like 4 in 1. Okay, so that can mess you up. If you ever try to plug one of these cables in to a input jack meant to accept this type of cable, you might have to tool with how deeply penetrated you have it in the jack, because the wrong contact points are making contact with the input. That's what's happening there. So start looking at all of your cables, because they're trying to tell you something. Okay, here are some common unbalanced cables. This is what I live with, right? Guitar cables. So if it's long, it's usually called an instrument cable, and if it's super short, it's just a patch cable. You're just connecting from one device to another. Like this. This is how it usually goes. Right, here's your guitar. You take an unbalanced cable, and then you can plug it into your effects. And the effects are right next to each other, so you just have a little patch cable. And then you take another instrument cable and you go to your amplifier, and you have a whole signal chain. The speaker cables are fundamentally different than the unbalanced cables, even though they look the same. Notice here that we have a phono plug, and it just has the tip and the ring, right, separated by the little piece of rubber there. However, because speaker level is so robust, so large and strong, it doesn't need shielding. So if you split open your speaker cable, it's not going to have this metallic mesh protecting it. All it will have is 2 cables, and those 2 cables are transferring a positive and negative version of the signal. So if you've ever set up your stereo or tooled around with speakers, you may have noticed a black and red wire. So one signal is shoving the speaker cone forward, and the other cable is shoving the speaker cone backwards, right? Push and pull, thereby creating the compression and rarefaction wave analogous to the analog audio. Like I've done, as a kid, like trying to figure out cables. So I had accidentally plugged in a speaker cable into my guitar and then was dumbfounded by the lack of results. It was noisy. Like, I put the cable in and then took it out halfway, and then I could kind of hear it, but then it cut out. I was like, what is wrong with this cable? So usually what you got to do is see this portion of the cable here right by the plug. It'll typically say speaker or instrument. Now, happily, the technology of speaker cables has pretty much abandoned the phono plug. And what you will encounter and speak on, I think that's a brand name. So yes, these are both speaker cables, but this variety here locks into place, which means that you plug this into your speaker cabinet and you twist to the left or to the right, and then it just can't come out, which is good because if your speaker cable comes out, this is a large amount of amperage flowing through these wires, and that could cause the next order of business to fall apart. And this, of course, is impedance. So let's return to this picture of electricity, right? So the different analog signals are differences in voltage and amperage. But when you get into setting up speaker systems, it's important to begin considering ohms or resistance, right? So now these big speaker systems, depending on how you have them set up, will offer different levels of resistance as measured in ohms. What the heck am I talking about? Okay, so let's imagine this. On the left here, I have a power amplifier. Now, if you send your speaker level out of your amp to a speaker enclosure, from this speaker enclosure, the signal is then routed once more to a second speaker enclosure. Such a system is said to be set up in series. Now, I don't know if you've ever experimented with this, or in science class, if they ever gave you a battery and a string of lights, and you could hook the lights up in a circuit called a series circuit. That's what this is. This is a series circuit. It goes from the amp, and it goes to a speaker, and then it goes to another speaker. Now, as it happens, this method of hooking up speakers creates more resistance or a greater ohm load. The opposite is true if you hook up your speakers in parallel. Now imagine our power amp again, but now we're sending its signal to this speaker, and then the power amp is sending from a different output another analog signal to another speaker. So if you unplug this one here, this one keeps playing, and vice versa. If you unplug this speaker over here, the one on the right will keep playing. Such is not the case for a series circuit, right? If you unplug this one in the middle, this one over here shuts off. There's no way around it. So what we have is a fundamental difference in how to hook up your speakers. One's called a series circuit, and one's called a parallel circuit. And their primary difference at the level of impedance will be their ohm load. Okay, we're crossing the finish line here. Let me briefly go through a few details on ohms. Obviously, if you're going to hook up a system in parallel, you need two outputs. So here's the back of a power amp, and notice that it has, not only does it have two inputs for a left and a right from your mixing board, but it also has two outputs. So you need at least two outputs to hook up that parallel circuit. Here's my shorthand I came up with. If you are hooking up speakers in series, then the more speakers, the higher the impedance. And conversely, if you are hooking up speakers in parallel, then the more speakers, the lower the impedance. So that means that this system here has lower impedance than this system here. Makes sense. The electricity has to perform a duty in this speaker, and then it's all tired out from performing that duty. It's like, oh man, I still got to go to this speaker, right? So that's more resistance, greater ohms. Whereas in the parallel circuit, it's just the electricity just has to go to one speaker, do one job, and it's all done. And on the other side, it just has to be sent out to one speaker. It does its job, and it's all done. Okay, so if you look on the back of speakers and on the back of power amps, you'll notice some details. The critical detail is that speakers will give you a resistance reading in ohms. See how it says 4 and then this goofy looking horseshoe? That's like a Greek letter for omega. 4 ohms. Speakers have a very precise impedance. They tax electricity to this degree. Whereas a power amp, see here in the bottom right, it gives you a range. It's like here's 2 ohms, here's 4 ohms, here's 8 ohms. So you have a couple different options. Here's how it works. If you have two 8-ohm speakers and you have your circuit wired in series, it doubles the impedance. So each one of these is 8. 8 times 2 is 16. So that means that you have 16 ohms of resistance in a series circuit with two 8-ohm speakers. If, on the other hand, you have those same two 8-ohm speakers wired in parallel, then the impedance goes down by half. So now those two 8-ohm speakers are generating a 4-ohm load. Okay, so this is important because if you have a power amp that's set to handle 8 ohms, say, you have two 8-ohm cabinets and you have them hooked in series, do know that you're drawing, that's a 16-ohm impedance. So if it's series, then it's twice as high. If it's parallel, then it's twice as low. So 8 ohms becomes 16 ohms, and 8 ohms becomes 4 ohms in series. Look at it one more time, and then that'll be all for today. Pretend that these are two 8-ohm cabinets. This will be drawing an 16-ohm load on your power amp. And then if, on the other hand, you have it set in parallel, and these are still 8-ohm cabinets, now your impedance is only 4. Power amp does not have to work as hard. Okay. I'd be happy to entertain any questions. I know that was a lot, but uh, especially the speaker configuration stuff is fairly important because you can do damage if you don't have your ohms configured correctly. Okay. I hope that you got something from that presentation. I enjoyed giving it to you. But unless there are any questions, I want to wish the two of you a very nice and relaxing weekend. And take care, and I'll see you soon.